So here is another example for class number 11. Ball. Well, we're calling them billiards, I guess. I guess that's fancy schmancy for pool. And each ball has a mass of 200 grams. And for whatever reason, we're using a yellow cue ball. Actually, the cue ball is actually smaller than the other balls. I guess it doesn't have to be. It depends on the. If you're using one of those coin-operated pool tables, then it's smaller, so that when you scratch, the cue ball will return. But I think in general they might be just a little smaller anyway, even in regulation. But we'll continue on. If A strikes B with a velocity of 1.5 meters per second as shown, determine their final velocities just after collision. Ball B is originally at rest and the coefficient of restitution is 0.85. Neglect the size of each ball. Okay, it's because they are particles, and that's what we do with particles. Okay, so we have this thing set up, and we will draw them out as diagrams here. So this is the initial, here's the impulse, and here's the final. And I didn't leave enough room, kind of ran into this thing here. So here's the impulse of those two things happening, and here's the final of them, and I didn't leave much room in here. So this guy has an initial I will draw as a dash line that's coming down here, but he's got here's my normal coordinates right here, and here's my tangential coordinates. So he's got I'll draw it in here, mass of A, velocity of A1 in the tangential, and here's mass A, velocity A1 normal, coming around down that direction right there. They have a collision, kaplooey, and now this one, and we know the direction it's going to go. This is the mass B, velocity B2, and we'll just call it normal, but it's the entirety of this thing. And but this one is going to have the mass of A, let's call it velocity of A2 tangential. And which way did I draw it? This way. I decided to draw it this way right here. I said that it's going to have mass of A, velocity of A2 normal. I decided to keep it going. Let's say that it keeps going. It could bounce off all the way back, but let's assume that it's going to go to the left right there. And we could actually, if we wanted to be nice to ourselves, let's make normal in that direction and tangential in that direction. Make everything positive. We could choose anything we want it to be, as long as we're consistent with the thing. So let me see a little preliminary stuff. Let me say that my A1 in the normal direction is going to be 1.5, and so it's going to be cosine of 40 degrees. And that ends up equaling 1.149 meters per second. VA1 in the tangential is 1.5 times the sine of 40, which is 0.942, no, 9642, excuse me, meters per second, which is actually equal to tangential, the second tangential, right? That equals that. We know that that's, so we already know what this value is going to be. We didn't actually have to draw that into right there. We just know that has to equal to that. It has no other choice. Okay, so now in the n direction, right there, we take this, and of course we decided that they were going to be yeah, I get that right. Nothing else over here, nothing that happens right here. These are equal and opposites, so they cancel out. So it's going to be equal to, we're going to say MB times VB2N We can even just drop writing that, just say VB2 if we wanted to. And then I said plus my VB A. So there you go, A, this guy right here, A2. And I forgot to write it. I'm going to cancel them out here in a second. MA VA2N. All the masses are the same. So we're totally golden right here. And this guy right here, we know this answer right here. So we're going to put them in as 1.149. It's going to be equal to VB2, I'm dropping the N, plus VA2N. It's going to be my first one. Then I take the coefficient of restitution in the normal direction right here, and I say, I'll write it out the right way. VB2N minus VA2N divided by VA1N minus VB1N. And this one is 0 right here, right? And this one we know, so I'll write this out. VB2, all right, so its entirety, VA2N divided by 1.149 right here. I didn't leave enough room to say equals coefficient restitution 0.85. So I can write a second equation here where I just say VB2 minus VA. Yes. I switched my ends and stuff in here and when I wrote the other thing. And that's just the 0.85 times our 1.149. So that equals 0.9767. And that's equation 2. All right, so we'll just ignore that little thing right there, that they equal. So we go solve 1 and 2 right in here. And if we do that, I didn't bother writing the whole thing out. VB2 is going to be equal to 1.063 meters per second, and it was positive, so it was going in the direction, of course, we were pretty sure it was going to. And then VA2N is 0.08618, so it got really small right there, so it dropped down. So if we want to find the velocity of A in the second one, right, we take the square root of the original velocity in the tangential, in this case it's x direction, and 0.08618, and I predict it's not going to make a big hill of beans. 0.9680, right? So it didn't change it much from what it had right here, meters per second. And if you want the angle onto the thing, this is, we'll say angle A2. We will take the inverse tangent of, this is the this is the rise in this case right here, right, onto the thing, because that's the vertical direction, and it will be coming down this way right here, because we did get a positive thing here. This is still coming down this way, so the quadrant will be in the lower left-hand quadrant. 9642 divided by 0.08618, and 0.9642, 0.08618, and you take the inverse tangent of the thing, and we get like it's 84.88 degrees right there. So the answers for the velocity of VB2 is going to be 1.063 meters per second, and with the arrow that makes it a velocity. And then the V A2 is going to be 0.968 meters per second. It's coming down that way at an 84.88 degrees. So pretty much straight down. And let's hope that the hole, one of the holes in the pockets, that's what they're called, one of the pockets. Let's hope that the pocket isn't in that direction right there, because we'd scratch.